All right, guys. Before we start chapter 8, I know that we planted the seed here when we're talking about chapter 7, as we provided a missing link for metabolism. Now we know how oxygen gets in and how everything else happens in order for us to maintain homeostasis and also adjust energy demands as the environment changes. Chapter 8, we're going to discuss changes that happen specifically to the cardiorespiratory system as it pertains to changes in the environment, specifically to exercise. And for that, I have to introduce Adolf Fick here, a German physician that lived in the 1800s, and he's responsible for a couple of two very big discoveries in the field of physics and physiology. One is the Fick's law that we have talked about on chapter 7. We're talking about the solubility of a gas is dependent on the composition of the molecules of that gas. There's only so much oxygen that can be diffused into a liquid. There's only so much CO2 that can be diffused in a liquid, and so forth. So he's responsible for kind of generating that law, as well as, and more applicable to us in this context, is the Fick principle. And the Fick principle is going to be the formula that we still use today, sometimes also known as the Fick equation, which is how we are able to determine the amount of oxygen that is used by tissues at any given time. So the book definition there, oxygen consumption of a tissue is dependent on blood flow to that tissue and the amount of oxygen extracted, which is represented by Q times a VO2 difference. Q stands for cardiac output. We have discussed that with chapter 6, and we will do some discussions on other changes into the cardiac output on Wednesday in class. And then the AVO2 difference, and we did an exercise in class last Friday to determine AVO2 difference from rest to exercise. Both are extremely important in determining the amount of oxygen that is consumed by a tissue. For that, I'm gonna try to create a creative way to illustrate this, and of course, take with a grain of salt the accuracies behind this, because I know in this example here, both are gonna be moving. But I'm thinking about the flow of traffic as people are leaving a concert, right? So people are leaving a concert nowadays, not even taxi anymore. We're calling that Uber. As people come out, we're gonna have a matching demand. But a problem is gonna happen when we start having more people coming out of that concert than transport being available. So the more people that come out of the concert, and if the method of transportation is not capable of keeping up with the demand, we do not have enough cabs, and we're going to have some people that are going to be very happy, and we're going to have some people that are going to be pretty upset. So the flow, the things can be taken away and utilized. For example, we are utilizing here, we are servicing customers, right? So the ability is that we need to have cabs in order to satisfy our customers. So the number of cabs available is extremely important to make sure that everybody's happy in the situation. So second example is the contrary. When we have this huge line of cabs here, they're waiting for the end of the concert. They're expecting a pretty big show of people, but then they kind of have a trickle, right? So one person shows up and then takes a cab, another person shows up, then the third, and then a lot of people start going towards the metro line. A lot of people start getting rides, or maybe they were staying downtown in hotels. And then the trickle kind of slows down. And then all of a sudden we have all of these cabs over here that are there ready to be used, but there is nothing there that can fuel their service. So the whole idea here is that both sides of the equation extremely important to determine its use. You can think of the cabs as your mitochondria, you people as your oxygen. So in this case here, we have all of these mitochondria available, but there is not enough flow of oxygen to make the mitochondria to be used. In the illustration number 1 here, we kind of had the scenario where we had a lot of oxygen available, but not enough mitochondria to utilize that. So a lot of the oxygen went unused. So in this case here, there'll be a low AVO2 difference. In this case over here, there'll be a low cardiac output. In both scenarios, there will be a low oxygen consumption. One because the flow was low, the other one because the availability was low.